So just a few things to remember about kinetic friction before we hit static friction in a little bit more detail. Just recall that although this is the formula that we tend to use for kinetic friction when things are sliding past each other, on your formula sheet for the AP exam and so forth, this is the way the formula is written. And so we need to make sure we understand how to interpret this, that for kinetic motions, we use the equality part of that inequality, which will be explained in a few minutes. And then do recall that the value of mu sub k should be between 0 and 1 in all realistic situations. When we switch to static friction, we switch to a mu sub s to indicate that change in the problem or in the situation. Note that mu sub s actually can have a value greater than 1 and will always be greater than the value of mu sub k for a particular situation. Also, that static friction, like has been said before, cannot be determined purely by a formula in most situations. In most situations, you'll need to use F equals ma and infer its value by looking at everything else that's parallel to it. Its direction always opposes the intended motion. So again, you need to imagine what would happen if the object could move and know that static friction is the thing that's keeping that from happening. And so it's always sort of considering the possibility of motion in order to figure out why it's not moving. You'll also find that static friction allows motion in some situations in our everyday world. For instance, you cannot walk without static friction. It's not that your feet are sliding against the floor usually, so it's not a kinetic friction idea, but the fact that your shoes do not slip against the floor means that there's static friction, and it's actually a forward pointing friction that's causing your motion. Similarly, for a ball rolling without slipping, there is a static friction that keeps the object from slipping along as it rolls or as it spins. That direction can be a little bit trickier to determine. We'll look at different examples throughout the year. Just want to look again at that case study from the earlier video and make sure that we're understanding sort of mathematically how we're going to approach things. So if we were to pull a block with some sort of an applied force, as we increase that applied force, the frictional force will also increase up until the point when it actually moves. This is all static friction. This is all a responsive force. You cannot determine the value of that static friction without knowing the other things that are happening. Its value will always, though, be less than a certain maximum value that occurs right when the object breaks away, the threshold point when things start to change from not moving to moving. And that moment, that force, that's the only one that can actually be calculated using the formula that we often see, the mu times the normal force. Up until that point, the value of static friction has to be inferred from all the other forces that are acting. In problems, you look for phrases like breakaway point or about to move or first begins to move. That is all indicating that you're at this particular moment in the situation where the frictional force does actually equal the maximum value of static friction. And you can use mu sub s times the normal force. And then after it begins to move, and at any point when an object has motion relative to whatever surface it's touching, there's going to be kinetic friction only. You can never have both kinetic and static at the same time. Either the object is sliding on the surface or it's not sliding on the surface. And if it's at the point when it's about to slide or it's just beginning to slide, that's when it's in this situation here.